cloud. Let's see if that's working. So that should come up with a pop-up and everybody should see it. So some people had some issues with the homework, but not all of them showed up today. But what I would say is that we've got a weekly homework assignment. Let me see if I could just run through the rest of the class, because I think everybody needs to be aware of what's going on here. I've released homeworks. Yesterday we had a homework that was due. It was homework 8. I've extended it till the evening tonight, but I'm not going to keep doing that. So, you know, you got an obligation to the course to do a weekly homework assignment. And I appreciate it if you guys could just do it on time and not keep coming back to me saying, please extend it. Deadline's a deadline. And here's how we're going to run it. Every week, we're going to have a homework. The rest of the homeworks will take us till homework number 12. Homework number 12 will be the last homework of the course. So from the point of view of Blackboard, I think everybody should be able to see all the rest of the homeworks. So there's no surprises. All the homeworks are now available. And you should be able to do them at your own pace. Just don't wait till the last minute to get them done, because it doesn't make any sense, right? You got a lot of time, got a whole month to finish a month's worth of homeworks. And the way I got it figured, you had your homework 8 due yesterday, but now you got it due end of day today. So that's like midnight. And then on the 5th of April, which is Wednesday, homework 9 will be due. And then on April 12th, you'll have homework 10 due. That's this one here. Then on April 11th, you're going to have homework 11. No, sorry, April 19th, you're going to have homework 11 due. And then on April 26th, we're going to have homework number 12 due. That is going to be your last homework right there. And that's on JDBC and servlets. So that's a server-side Java technology, servlets, and JDBC will give you another architected tier. So it is like a what you call a 3-tier architecture. You've got your client, which is, you know, looking for HTML from a web server. The web server is dynamically generating the HTML using the servlets. And then there's another computer, could be a different computer, that runs your relational database management system. And the interface to that is going to be JDBC. That's the Java Database Connectivity API. So then, when you look at like your academic calendar, May 2nd and 3rd, those are your reading days. So basically, the semester is over with your final, and your final is going to be May 17. It's going to be a Blackboard-enabled final. It'll be a mashup of the prior homeworks, and you're going to have 2 weeks to do it. And it won't be a timed final, but it will have a deadline, and the deadline will be on the 17th. So you'll get to do it. You know, you can print it, you can touch it, you can play with it, you can mark it up, and then keystroke it in. It could be 100 questions or so. So at some level, it's a big thing, and you don't want to wait till the last minute to get it done. And you'll get 2 attempts, and you get the highest grade of the 2 attempts. And that's the long and short of the final. And it's not been released to you yet. So what you have now in front of you is homeworks 9, 10, 11, and 12 for April 5, 12, 19, and 26. So if you go to homework 12 right here, and you look at the options, you'll see it's, yeah, the 26th. So you can see it's 5, 12, 19, and 26. And that's got to be homeworks 9, 10, 11, and 12. Does that make sense to everybody?
Yeah, it does.
Cool, cool. All right, so what we'll do for May 17 is we'll have 2 weeks in which to do our work with the final and go over any sort of questions that you may have, you may or may not have, and that is probably my way of saying after Easter break. This semester is going to end incredibly fast. I mean, just amazingly fast. And so Easter break, now that I'm on this topic, is, I think it's the 6th. Let me just check. You guys, yeah, it's 6, 10, 6, and 7, 6 and 7 in April. So these 2 dates, 6 and 7, we have a break. Now, are you guys able to meet on the 6th, or shall we skip it?
I should be fine. I don't know about anyone else.
Well, I got, it's a Jewish holiday, it's Passover. It's kind of a holiday for me, but if you guys want to have a meeting, I will meet. Otherwise,
If it's a holiday for you, Professor, I don't think we should meet.
yeah. All right. Well, all right then. We'll have the homework due the day before anyways. So that's fine. The homework will be due on the 5th. And I don't think we need the meeting on the 6th. And of course, all of the lectures are recorded and embedded inside of the homeworks anyways. So you've got your lectures there. So that's the way I'm planning to wrap up the course. Any comments or questions about how we're going to finish up? No? All right, so then the way I figure it is, you guys got a homework number 9 coming up. So let me just sort of say a couple words about that. RMI is remote method invocation. It is the critical enabling framework for allowing us to do distributed computing. So when we use RMI, what we're really doing is we're looking for client service relationships where the client is looking for some kind of computation and the service is doing the computation. So what you could do is you could make the rough analogy that it's distributed computing with a network of workstations. And so what that means is that every workstation will have its own memory. It'll have its own CPU and its own, perhaps multiple CPUs, and maybe even its own file system. And as a result, if you can find a way in which to segment the task so that you're not overwhelmed by overhead, then you could, in theory, put in 10 computers and make it 10 times faster than just one computer. And I know that sounds patently absurd because there's always overhead, but you need to find an embarrassingly parallel program in which to do it. So not to put too fine a point on it, if you were, let's make up an application. If you were Disney and you wanted to make a movie and every CPU needed, I don't know, make up a number, an hour to render a frame, well, then your 10 CPUs should be able to render 10 frames per hour, whereas one CPU can only render 1 frame per hour. So if they're all working at the same time on the same movie, but they're working in different frames. They can all have their own copy of the geometry. They can all output their own images, and they can all essentially do image sequence processing as an ensemble of machines where everybody outputs an image with an image frame number, and then later the frames are assembled. So that's the bird's eye lowdown on the RMI caper. And so the rest is all detail. What I did in here was I put up a paper called the RMI code generator. And I also gave you an introduction with PowerPoint to chapter 43, which is in the book. So one of the things that you might like to do is take a plain old Java object that's called a POJO and convert it into a remote method invocation capable object. And so converting classes to RMI, doing data structures over the network to transmit RMI classes, these are all subtleties within the RMI framework that will enable you as programmers to take advantage of Java as a truly distributed computing system. So from a network programming point of view, this can be a big win for you guys, because what it gives you is a mechanism by which you can do supercomputing. So if you wanted to build a supercomputer, let's say out of, I don't know, make up a number, 25 different printed PCs in a lab, you could get them so that they all cooperate together on a local area network and give you the ability to run your code in parallel. So it's a key to doing parallelism. And CentaJ, which is my own coined term for a program that writes programs that enable plain old Java objects to become distributed objects, allows you to take advantage of multiple machines and do your computation in that way. So that's the basic idea, such as it is. I had a lot of sort of I'll say slides that I could take you through, but it's kind of a PowerPoint death march, and I don't think it's really helpful to have you guys just sit here and sort of listen to me pound through a bunch of PowerPoints, especially since I've already got that as a Vimeo video for you guys to watch if you want to. There are a couple of subtleties in converting an instance of an object into an aggregate object. And one of them is that you can have conflicts between the various methods. So if you have two methods that collide, then you have to, when you shadow them through what they call a delegate, you need to disambiguate which methods are which. So imagine, if you will, if you have multiple inheritance, the two base classes from which you inherit both have the same method. Maybe one is called display and the other one is called display. And so then when you invoke display from the subclass, the question is, what gets displayed? And it's not clear. If class A appears before class B, then maybe class A has its display invoked. If class B appears before class A, then maybe class B has its display invoked. And so this is a fruitful source of bugs because it is what they call topological sorting. So we don't have multiple inheritance of implementation as a result in the Java programming language. But when you're wrappering a bunch of different classes together in a single class and exposing all the methods at the same level, then you have to disambiguate the different classes. So for example, here you can see the dialog box says, well, which equals do you want? And you have to pick the equals from the correct, like here's date equals versus string equals. They both say equals. We don't know which one you want. So when you're bringing these things together and making up a wrapper automatically, you have to do the disambiguation. And so I go through that in my work to show you guys how that's all supposed to function. So that's for when you're trying to take plain old Java objects and make a mashup of all the different objects so that you can remotely invoke them all in with one wrapper. And that is that's really what this paper is about. If you watch this video here, you'll see all the YouTube videos for chapter 43. And the other thing you want to do is you want to read chapter 43. And so that's kind of important because it'll help you with the questions here. So that's well, let's see, it's only 20 questions and you get 3 attempts. Wow, 3 attempts. That's generous. So here's an example. What is the function of RMI? It enables programs to be invoked in a remote address space. So you've got protected memory, you've got your own address space. Everybody gets to do an invocation, and what's returned is an instance of a class. So you're getting an entire data structure back. Now to do that, the instance of the class has to be serializable. In other words, you've got to be able to take an instance of a class and get all of its members and all the data that's in there and marshal it across the TCP/IP socket-based network in order to pass it from one place to another. So if you think about sockets as an unformatted sequence of bytes, an instance of a class is the format for that sequence of bytes. Moreover, if you took an object output stream and redirected it to a file output stream, you would be able to save that instance to a file. That is the mechanism of serialization. So RMI can only work because of serialization. So that's a critical underlying technology that RMI takes advantage of. Instances of objects are serialized so that they can be written to object output streams, which are then directed into a network. And then the network will transmit those object output streams to a receiver, which reconstructs the request for the invocation. It does the invocation, takes the answer, serializes it, and passes it back. And you can read about this in chapter 43. Am I making sense? You guys understand what I'm trying to say here?
Yeah, I'm listening.
Cool. So MIMD, you may have had my architecture course, maybe you haven't. In the Flynn taxonomy, we have SIMD, MIMD, MISD. MIMD is multiple instruction, multiple data, and that is essentially what you're getting when you're doing RMI. Everybody gets their own instructions for each machine, and they all get a copy of their own data. SIMD is when you have single instruction, multiple data. That's when you have a vector machine. So vector machines are like digital signal processing chips, maybe what they call Altivec coprocessors, which are built into PowerPC, or multimedia extensions, MMX processing instructions in Intel, or SSE or SSE2, which are streaming SIMD instructions. Those are all examples of a way in which you can get fine-grained parallelism, but it only works when you're doing a single instruction on a homogeneous set of data. That means that you got a vector or an array of all the same data types, and you want to take A plus B equals C, where A, B, and C are all arrays of integer. That's a vector process. That's SIMD. But what you're doing with RMI, that's MIMD, different architecture. MISD is multiple instruction single data, which is good for checking computations to see if there is any error. And SISD is single instruction, single data, and that's what happens when you have a single CPU doing one instruction at a time. So you're basically doing MIMD architected work when you're doing RMI with MIMD. Every time you do an invocation remotely, you can throw a remote exception. So that means you'll be on the computation server, something goes wrong, you divide it by 0, you throw a remote exception, and the caller gets the information that you tried dividing by 0 on the computational server. So you have to have a way to throw exceptions remotely so that your server can be notified when things go wrong. Otherwise, you could invoke something and say, please go compute this for me. And then, the computation server says, uh-oh, he's dividing by 0. It's impossible. You can't divide by 0. And it just dies. Well, that's no good, because then you didn't get any feedback about what went wrong, and you're just sitting there waiting for an answer. When you do this kind of computation, it is stop and wait protocol. You do the invocation, you say, please go compute it for me, and then you wait for the answer. Now, you might ask 10 different CPUs to render 10 different frames, and you'll have 10 different threads waiting on the 10 different CPUs. One of those threads could get hung up if it gets stuck. And maybe it got stuck because it ran out of memory, or it ran out of disk space, or it ran into a problem where it tried to divide by 0. I don't know what the issue is going to be. I can't imagine. Could be anything. But then at some level, it's going to throw a remote exception, and you're going to get that exception in your calling thread, and it has to be able to handle that exception and say, you know what, that didn't work. Let's try something else, or let's give up and give it a different job to do. So you're going to be importing java.rmi when you do this sort of thing, and that's going to give you access to the RMI framework. In the RMI architecture, you're going to have to unmarshal the data when it comes through. So marshaling the data means serializing it, sending it through the pipe, and then having it deserialized, or what they call unmarshaled. You're going to have to compute some kind of result. You got to send back the answer. You do not need to open an editor. So that's that. And then the steps for creating an RMI application, I'm not going to go through it now. If you go to page 677, you'll be able to see there are these different, if you want to do it by hand, there are 8 different steps involved in taking a plain old Java object and converting it into an object that you can invoke remotely. And one of them includes creating a wrapper. So I'm going to let you guys sort of watch the video. And if you go to the top in here and you say Intro to RMI, I think you should be able to click on it. And yeah, so there's a nice video here which will give you an introduction to RMI, and all of the code in this video is part of the course code. So if you go to I think it's network.rmi. You'll be able to find examples of all sorts of interesting RMI stuff. So here's an interface called computable, right? And so in computable, we want to compute something that will throw the remote exception that we talked about before. It has to give us an answer. The answer is serializable because it needs to be marshaled. It can print. You can invoke print remotely so that you can give it something serializable that gets printed. And we don't know how complicated the implementation for a computable object will be. It could be very complicated. It could take an hour. It could take 2 seconds. I don't know. The client over in here, he's going to try and invoke something with a computable object on a remote server. So he has to look up the server and execute the object on that server. The server does the execution. He just does the invocation. So he gives you an RMI protocol. It's just like HTTP, only he's using RMI. So because he's marshaling stuff across a TCP/IP network. So here comes the IP address of the remote compute server. He looks up the registry on that server and he wants to map it to something that is computable. And once he does that, he can do some invocations. And so, for example, over in here where he says c.println, this is cool, that should print on the console of the remote server. So strings are naturally serializable. They're just an array of bytes, actually. And then when you go over into the compute server, this is going to find itself as an implementation of computable. It is extending unicast remote object, which is part of the RMI framework. That enables it to be invoked remotely. Unicast is different from multicast. Unicast requires that you have a TCP IP address associated with the server, that you know what that address is, and that you'll be able to pass an instance of a computable object to the compute server given its IP address. And then once you call compute, it's going to return some string. You've reached Doug's compute server. It's kind of trivial. And it will return the answer, which you can print on the client. Also, you can invoke on the server the print line where it says hi from the server or whatever, hello world, whatever you like, and it prints it locally on the console. So it proves the communication path exists. And so that's a sort of a trivial example of being able to do some simple RMI invocations. There are a couple of things about IP addresses which I would call housekeeping. So if you go to the Internet Address class, and that's in the .NET package, you can get the local host, look up the IP address. You can take the address and you can bind it with a registry so that things can be looked up. So binding a URL with a compute instance, your compute server instance, is something that you can do so that when somebody comes to your IP address, they can look up your compute server and then start to do invocations. So it's a little bit involved, but once you get the hang of it, it's not too bad. And I give you examples of that. And then there's the book, chapter 43, which we can get into if you like. So I gave you a tic-tac-toe distributed service so that you can play tic-tac-toe using RMI. It's not particularly interesting, but there it is. You can do some image synthesis remotely, which is kind of neat. And then what I like to do is I like to take all the CPUs and somehow arrange them so that you can kind of see what it would look like if you had a whole bunch of CPUs online, give them each a busy light, and maybe IP addresses and CPU types, and then you can go through and update them and start to delegate. So here you could imagine there's a lab full of computers, and you want to use them all for your little supercomputer project, which may do nothing other than, render a bunch of images for your movie. It'd be really nice to have all 28 computers on and working all at the same time. Right now, they all have load 0, and there's no actual computers hooked to this yet, but that doesn't matter. So that's the kind of interface you'd like to have in order to be able to sort of give yourself a graphic user interface that controls all of the different computers. This is an example of what somebody did. They wrote a little Pong server that allows them to play ping. What do they call this? Pong is a game from the 70s, a video game, but you can play it using RMI. So that means you need a game server, which keeps track of the position of the ball and the position of the panels. And also you need a way to keep the score consistent so that when things are being returned, you can see that they're being returned. This is a way to invoke a mouse remotely using RMI. It's just something I was playing around with in case I wanted to be able to do a remote control of another person's mouse. And This is the remote job system, which uses a lookup server so that if you're running a screensaver, it will enable you to volunteer the CPU when it's idle, so that it can be used for CPU intensive tasks. So toward that end, what I did was I created a series of papers, which you can actually look at. All the papers are right here. And this is a screen server based system. So what we're doing is we're waiting for the computer to be idle. Let's see if I can get it. Screen. Here it is. Heterogeneous autonomic screensaver for CPU scavenging. And so this enables you to have the CPU volunteer itself when it's running your screensaver, so that it can be invoked remotely by a lookup server. So it volunteers itself to the lookup server. You go to the lookup server and you ask, are there any idle computers out there? And it gives you a list. So by running the screensaver on the different computers, you're able to effectively take advantage of the fact that you have a lot of idle computers available. And so what we did was we set this up as a Java Network Launch Protocol or Web Start application. And then all you had to do to run the screensaver was go to the .java website and run that application. And all the rest of this is sort of like, I'll call it housekeeping details. But you can kind of see the big picture overview where there's a lookup server. The user PC goes to the lookup server and finds a whole bunch of other computers that volunteer themselves as able to run remote method invocation computable implementations. So you create the computable implementation on the client, and then you can send it to any one of a number of different servers. And so that's that was the theory. And so we built a system for doing just that, which is kind of neat. And we had a bunch of people doing thesis work on it. And that thesis work is still interesting. So if somebody was interested in doing it, we could do that sort of work with you. So that's the, there's another screensaver in there. Here it is, Saver Beans. So now we have all the different platforms, all of them. Well, not the mobile ones. So Windows, Unix, and Mac, with screensavers for all of them. And so we created a Mac screensaver, a Unix screensaver, a Windows screensaver, and you can see them all are listed right in through here. And we just kept going through and building up our system for doing this. So you can see it's been quite a long project, quite interesting. And I'd love to do some research with you guys if you ever want to get into that sort of thing. So that's what I've got. Are there any questions about this homework or chapter 43?
I haven't had the time to look over it yet, so.
Yeah, please look at chapter 43, give it a read, watch the videos. I think it's important that you do that sort of thing if you want to get something out of this course, because otherwise, you could just sit there and I guess you could play around with the blackboard and you get a grade for sure, but you won't get much out of the course if you don't read the book and watch the videos. So that's kind of important. Let me see if any of these videos have any problems. This one's only 10 minutes, so it's plain old Java object to RMI conversion. So yeah, it looks like it's only 10 minutes. And so you can definitely take a little time and watch some of these videos. I'm not going to bore you by playing them for you, especially through Zoom, because that always doesn't work. And that's what I've got. I'm going to try another one just to make sure this is working. Yep. There, Now, that one's an hour and 15 minutes, so that'll take you some time to get through. But if you watch these videos, you will learn all about RMI and some of the work that I've been doing, which I kind of think is sort of an interesting thing. We got deep into it. If you guys want to get deep into it with me and do a research project, I'm all for it. But that's what I've got. You got any questions for me? Josh, you came in a little bit late. Did you get the part about homework 8 has been extended till the end of the day? I don't know if you can hear me. You're muted. Well, anyways, are there any questions? I'm going to ask you all to unmute so I can hear you.
No questions.
I don't have any questions either, Professor.
All righty then. Well, then I'm going to wish you all a good evening. And I want to thank you all for your, your attendance. And please keep in mind, we've got a weekly homework assignment. So have a good evening, everyone.
Thank you.
Thank
Have a
you.
good night.
Bye-bye.
Thank you, Professor. Have a good day.
You too. Bye-bye.